Hey, hello everyone. I am Martin Jonas from Ferget Labs, and with me is Ramon Amela from Rooftop Labs. We are presenting today a demo of a zero-knowledge proof verification on Bitcoin. So, first of all, how does BitVMX work? Well, BitVMX is a protocol that allows to log funds in a transaction in Bitcoin, where the spending condition for this transaction is the result of the execution of agreed program. This is a big difference on how usual transactions works in Bitcoin that requires the sign of this transaction. Uh, this this allows, for example, for two parties to define a program in a setup phase, and later on time, when the input of the program that satisfies this program is presented, the logs will be available. So at the beginning, the participants will need to collaborate and sign a set of transactions, and that will be used to in the dispute resolution protocol if necessary. At some point later, one of the parties, in this case the prover, when she wants to withdraw the funds, will kick off the transaction presenting the input, and the input is the input that makes the particular program return successfully. As the verifier is monitoring the Bitcoin transactions, will see the input presented and committed by the prover, and will take this input to use it on his local machine to execute and see if the execution is correct. If the verifier detects some cheating, will start the challenge protocol. So for this, we will be using an execution trace. Basically, this trace is we will hash the state transition of each operation of the CPU. And the goal of the verifier is to find one step on these state transitions where the hash mismatch. So for doing this and speed up the search, instead of using directly a binary search, we are using an NRE search to dissect the whole tree of execution. Using this, we are going to verify a zero-knowledge proof on chain. We are taking advantage of the BitVMX CPU implementation that is a RISC-V implementation in this case. Basically, this implementation allows to execute any arbitrary program off-chain and verify that execution on-chain. I mean, it allows to challenge any of the steps of the execution. In particular, in this case, we are going to verify a gross 16 zero-knowledge proof. How we do this? Okay, we are using a Docker to build the zero-knowledge proof. We are using a sample a sample proof produced with a RISC-0 virtual machine. We took a verifier made in C by the Citria team, and we are compiling this C file into a binary of RISC-V. Then we can execute this binary into the BitVMX CPU, and if necessary, any of these steps can be challenged on-chain with Bitcoin script. So to do this, we have a Rust program, an emulator that has several functionalities. One of these is generate the ROM commitment. So we pass the binary produced, the zero-knowledge verifier. This will generate the commitment. This means the ROM commitment that both parties agree of the program itself. At a later time, when the input is received, the same emulator allows to execute this binary with the input provided. And in case of dispute, also allows to search for the specific steps on the trace that may contain the error. Tries to find that step. Also, in parallel, any of these steps can be used to validate the execution on chain. I mean, on chain in this case will be done in a Bitcoin script emulator. I mean, that a functionality also emulator, but of course, then the Bitcoin transaction will be put on the Bitcoin chain. This is an example of one of the instructions, several instructions from the RISC-V emulator. In this case, some of the arithmetic operation. As you can see, you have the subtract, XOR, and or add, and basically it gets and generates the trace that we are talking about, where we have the read values, the transition for the made by the operation, and finally the write result. As part of the same process, we have the verify. This is what allow us to test locally in the same machine with the emulator of the Bitcoin script. Basically, we load the trace in the stack of Bitcoin. We transform that read with the operation, with the specific operation. We have mapped all the operations for RISC-V in Bitcoin script, and then compare if the result from the write equals the one produced by Bitcoin script.
Hi, my name is Ramon, and I research engineer at Rootstock Labs, and I will explain you how the previous explanation done by Martin has been actually implemented on the protocol side. So basically, we have designed two microservices, one for the prover and one for the verifier, that I'm running them in the same machine, but could be executed just through a network, and this how it should be done, in fact. So now we restart them, so we have fresh executions, and the first thing that we need to decide is who will be lying, let's say, because as Martin said, if there's an agreement on the result of the final execution, the protocol is not triggered. So what we will do now is we will consider that the verifier is lying and having a bad execution, more precisely in this step, that is 1 billion and something. This way, the hashes will not be equal. When the verifier will see the published hash on the prover side, will disagree, and they will do all the challenge response looking for the wrong step. And finally, the verifier will reach the conclusion that the bad step was an execution step, and the prover will be able to execute this step on chain to prove that he was right. This is done by setting up a program, and this is an ELF that has been compiled through RISC-V, and that both agree. And to run this program, we'll use the emulator that Martin just presented. Finally, we need to choose the network. In this case, we are in testnet. We have the total amount of satoshis that will be logged into the protocol. So the party that wins will get the remaining funds. And that's it. So let's begin. We can open the Swagger, and the final setup that we need to give to the protocol is the maximum amount of steps, because we know the program, but what BitVMX requires is to fix the limit of steps that we need to perform these computations. Since we know that in this case it's more or less 4.5 billion instructions, we have set it at 5 billion. So we trigger the protocol, and we can see here that things are happening, and basically the first part consists on the sharing of this call here, meaning that the prover is telling to the verifier that a new setup has started, so the verifier can start building all the data structures that it needs. And afterwards, the prover will ask to the verifier for the public keys. This is necessary because this way, with all the public keys that will conform the scripts, the prover will build all the transactions with these keys. And it's exactly what's being done here. So basically, the prover asks for the public keys, the verifier responds, and now we are building the 400,000 instructions that are part of this program. And with this, the prover will be able to build all the transactions, included the one that executes the scripts forming the 400,000 leaves in the Merkle tree. now we'll wait a little bit because since this has 400,000 instructions, it takes a little while to compute the Merkle root. Okay, so at this point, we see that the Merkle root has already been computed. So since all the transactions have been generated, the prover can generate the signatures for the transaction. So we can ensure that the funds follow the protocol chain and are not sent to another address. And in this step, what it happens is that the prover will send all the signatures to the verifier. Then the verifier will check that the signatures are correct, so that the verifier will be able to publish correctly all the transactions afterwards when it needs to do that. And if this happens, and in this case will happen, it will sign all the transactions and send back the verifier signatures to the prover. And once this will be done, the prover will be ready to lock the funding funds in the commitment transaction. One thing that I missed to mention before is that in this case, we are using 3 bits to choose the wrong step, meaning that instead of being a binary search to look the wrong step on the whole trace, we are using 3 bits, meaning that we are using 8 hashes. So we are able at each time to divide by 8 the amount of steps that are considered in the trace. So we'll divide the trace by 8, we'll choose one of the pieces that are defined by these equally divided hashes, and then we'll keep going down the execution tree. Okay, so at this point, the verifier finished to compute the Merkle root on its side and signed everything because, as we said, the signatures sent by the prover were correct. Since they have agreed on the program to be executed, that in this case is the SNARK verifier, both parties will have exactly the same program, so they will generate exactly the same scripts, they'll have the same exact addresses, and this way the verifier on its side can generate all the signatures, give all the signatures back to the prover, and once the prover is sure that when triggering the challenge can recover the initial funds, will do the funding transaction. So making a summary, the prover triggers the creation of the protocol, the verifier sends the public keys to the verifier sends back its public keys, the prover generates all the signatures, sends them to the verifier verifies that the signatures are correct, send back the signatures to the prover verifies that the signatures generated by the verifier are correct, and at this point, since they have both verified that the signatures of the counterparty are correct, the prover can perform the commitment of the protocol. And later on, when it has the input or whatever for the execution, the real execution of the challenge response protocol, will trigger the protocol in another call that we'll see afterwards. So at this stage, we already have the setup and we have both the prover and the verifier running, and the prover wants to share on-chain the hash resulting for the computation that we have agreed just before. In this case, what we'll do is come here, and for this setup ID corresponding to the one that we have executed previously, we launch the execute. And if we come here, what's happening now is that we'll start recovering all the transactions, and basically considering this hash here, we see that the execution is being performed. If we keep refreshing, we'll see these checkpoint files that start appearing one after the other, containing the result of the execution of the zero knowledge proof that is being executed with the BitVM emulator that Martin just presented before. Okay, so at this point, we can see that the prover have finished the execution, and we see that it took, if we refresh here, it's 4 billion and a half instructions. And we can see here that the hash has been transmitted on chain. And we can verify this by coming here. We can copy the instruction and it's still not confirmed, but we can already say that in testnet we have this transaction, and if we come to the details, we can see here all the values corresponding to the Winternitz encoding of the hash obtained after executing the transaction. We see the two microservices. We see here that we are processing a new step. That means that the verifier has received the notification from the prover. Remember that this could be just a cron, but too easy to speed up the demo, we make one call the other. And if we remember this hash, 5659, and we come to the verifier files, 5659. Here, now we see that the verifier indeed has detected that this hash has been published on chain and is on its side making the execution to verify if the hash is correct or not. So now the verifier has been executing the program after the prover published this hash here. We know from the previous execution that this should be something around this. So, okay, yeah, it finished. We see that the execution has finished, and the verifier, since we set up that the verifier was executing wrong this step here, sees that the final step is different regarding to the one published on chain. So it triggers the transaction, it publishes the trigger protocol transaction. That's the transaction that will force the protocol to be executed. And from this point, we'll see that the prover has seen that the protocol has been triggered and needs to execute some steps to publish the hashes on chain. So it publishes the steps, the verifier sees it and executes the same steps locally to try to search the first faulty step. So we are seeing this here, and as before, considering that this had already been published, we can come here and see that is unconfirmed, but is already in the pool. So the verifier can also already see it. And if we click on details, we see all the hashes here encrypted with Winternitz. So the verifier don't need to wait until this transaction has been published because will be accepted at some point. It can already chain the response. So what we see here is that we have the first iteration, some computations, the verifier sees the first iteration and publishes its choice. Then the prover publishes another iteration. The verifier sees it and publishes the new choice. And like this, we'll be narrowing the search interval in such a way that at some point, both the prover and the verifier will be, the verifier will be able to choose which is the exact step where there is a mismatching. we see here the publication of these hashes, meaning that we are already in the previous to last execution. We are seeing here the verifier checking which is the interval it's going to choose. Knowing that we are aiming for this one, it has already found it. So now the proved will execute the last 8 steps that are consecutive steps, and that will allow us to find the first real discrepancy in both execution traces. Remember that in the setup phase, we have defined that the amount of bits for the choice was 3. So at each iteration, the prover is sharing 7 hashes that define 8 intervals, and then the verifier responds with 3 bits number, specifying the interval containing a lower bound that is correct and an upper bound that is incorrect, meaning for incorrect, different from its own search. So now the prover has already published everything. The verifier will find the discrepancy step in here. It has already done it, and now the prover will publish the full trace. It has detected the first wrong step. It publishes the trace. Now the verifier will look at this trace and detect that indeed the error was in the execution of this step. So it triggers the transaction that asks to the prover to execute this on chain. And then what will happen is that if the mistake was on the verifier side, the prover will be able, as it will happen here, to execute this execution on chain and take the bond of this challenge response. If the error was on the prover side, he will not be able to execute this command. In order to execute it, we need to go to the tab tree with all the instructions. In this case, there are 400,000 instructions, so it's a pretty big tree, meaning that the computation of the control block takes a little bit of time. Okay, so now we ended up computing the control block, and indeed we have been able to execute the instruction on chain. Since the wrong instruction was on the verifier side, the instruction worked and the prover wins. We can verify here, as we did before, that the transaction is indeed in testnet. It has not been confirmed yet, but we can see this hash here, and we are just accessing testnet through public manner. And we can see here the necessary trace to execute the step on chain. And if we go at the end, we'll see here the codification of the instruction in Bitcoin script. Once we have this, with this, we executed the instruction of the zero knowledge verification on chain, considering that the verifier was lying. So this way, the instruction gets published on chain, but we can, at this stage here, execute a smaller program. We can go here, and instead of executing on testnet, we can execute on multinet to have lower, easier faucet, so we can get as many Bitcoins as we want, and the blocks are confirmed in 30 seconds. And here, since the execution is shorter, we're just fake that we are failing in the 50 instead of this big number. And now we'll show what does it happen if the prover fails. So we restart the servers. So the changes are uploaded to the server. Since I changed the elf that we are using, this execution will be much shorter. And we can come here. And now we do the same thing we did before, but now with just 1,000 steps. Remember that we need to set up the maximum steps that the execution takes. Come here. We have the same setup than before, but much shorter. Here we have already computed the Merkle root. We have here the init setup, the public keys, and shortly we'll see the signatures. So the setup phase is already finished. We come to this hash and we execute. We launch it and we'll see the same things than before, but much shorter. So the protocol has been triggered. The search starts. We can see here in the prover the hash revelation and all the steps. Since it's much shorter, it will take much less iterations. So here we are already in the last iteration and the trace has been published. And in this case, the prover, when it's forced to execute the challenge, we see that it's not possible and we obtain the equal verified, meaning that some verification that is done in the execution script is not fulfilled, meaning that the prover cannot execute the transaction. So after the timeout time, the verifier will be able to take the bonds. So as we announced, we have this challenge already done, but this is not hard-coded. We are able indeed to detect different challenges. So if now, for example, we say that we fake that instead of failing the execution, we are failing the hash computation. So we restart here. And now we execute the same thing again. So we generate the setup. The public keys. Something already shared. Now the prover is generating the signatures, sending them to the verifier. And here, that means that the signatures call in the verifier side is running, so it's verifying that all the signatures are correct, and for that needs to generate everything. So we're done here, and now we trigger this, and we'll see the same steps done before, but hopefully instead the verifier should realize that what's mismatching regarding its own execution will be the hash computation. So instead of triggering the execution on chain of one instruction, we'll detect that what's mismatching is the hash. But since this challenge is not yet implemented, we see it here. It will not, it doesn't work, but we demonstrate that we are indeed detecting it, and that is not hard-coded. So until here, the demonstration.